In this video, I'm going to go over simplifying radical expressions. We kind of touched on this at the very end of the video on notes number 35, talking about rewriting those expressions that were written as fraction or rational exponents into radicals. So that's what this first page is kind of talking about. It mentions the index of a radical, it mentions the radical symbol, and that number or whatever's inside the radical is called the radicand. All right, so all of this stuff is here on this page for you to refer to. Your most basic ones that you've dealt with are like the square roots and cube roots. This one's going to get a little bit more complicated, where you'll have maybe fifth roots, even sixth roots, fourth roots, and it will depend on whatever that index is, what kind of values are possible, okay? So I'm not going to spend a whole lot of time going through these different kind of charts here. I want to do some examples so you get a feel for how to do these, okay? Now, to make sure that we're fully simplified, this is kind of a good thing to make sure and check, is that no factor in the radicand is raised to a power greater than the index. So basically keep simplifying if that ends up being true. And the denominator does not contain a radical. All right, so this first one, part A, I can rewrite this to have each the numerator and the denominator can have their own cube roots. All right, so when I have the cube root of 125, I know what that is. That is 5. Now the cube root of 512, I don't know what that is, but if you go into Desmos, you could see that this is equal to 8. So the cube root, all right, I think I need to go to this one here. There we go. The cube root of 512, oop, sorry about that. Let's get into the actual radicand. Let's try again. Can I reduce that? Yes. Is 8, there we go, perfect. So this reduces to 5/8. All right. So if I do this next one, part B, I have the fifth root of negative 243. And that is okay that you have that negative in there, because if your index is an odd number, it is okay to have a negative power in there. So if I do the fifth root of negative 243, so fifth root, and I'll move over to negative 243, that's going to be negative 3. So I'm going to bring down that negative from the front of the radical. Then this was negative 3 for the fifth root of negative 243. And then I want to take a moment and just kind of think about the fifth root of m to the 10th power. All right, so if you think about this, we're trying to figure out m to some power when I raise it to the fifth power is going to give me m to the 10th power. That's how kind of I think the best way to think of this is, and you have the most success that way. A lot of students are going to learn this and be like, oh, just divide 10 divided by 5 to get 2. That's essentially what you do, but I want to make sure you know why we are able to do that, because if I go the other direction, if I have m to some power raised to a power that's multiplying, that's why you can divide to go backwards. So this will be m squared, and so the opposite of all that is going to be positive 3m squared. Okay, let's do the same thing for C. Now C, there's no index, so this is a 2. The square root of 81 is 9. And as we just found out with, if the numbers are divisible, right, if you take a look at these exponents, right, this 8 and this 10, if they are divisible by that index, you can go ahead and do that. It is, mathematically, will give you the correct answer. R to the 8th power, the square root of that is R to the 4th power. And S to the 10th power, the square root of that is S to the 5th power. Okay, D. This one I'm going to go ahead and expand inside first. Negative 3 to the 4th power is going to be a positive 81, right? Negative times a negative times a negative times a negative is an even number of negatives, so it's a positive 81. And the fourth root of 81, I know, is 3. All right, this last one inside here, this radicand, is called a perfect square trinomial that factors as x minus 5 squared. So if I take the square root of something squared, we've had this happen before in our units. That's going to, essentially, those are inverse operations of each other. So leave me with just x minus 5, all of that to the first power. So that's it for those first kind of 5 there. Let's keep going. Now I'm going to use some of these rules for radicals, the product rule, the quotient rule, which I've already kind of used part of these with exponents. It's very similar to the exponents. A couple of things here to note, and it has that please note, is that this is not okay. So we'll have that happen in B and C, right? So that B and C are fully simplified. You can't do anything with B and C. So if you check my key later on in Canvas, you'll notice that those are actually fully simplified. All right, let's do A. The square root of 9 plus 16, we can actually add 9 plus 16 is 25, and the square root of 25 is 5. So that one I can do. Let's do D. This is where I'm going to put them together as the fifth root of n cubed times n squared. We learned in that last video that if you have the same base and you're multiplying, you can add the exponents to n to the fifth power. And as we showed earlier, right, if this exponent inside and the index can be divided, you can go ahead and divide those and get n to the first power, or n. With this one, I'm going to give them their own radicals. So that's the sixth root of c over the sixth root of d to the 12th power. The sixth root of c I cannot do anything about, but I can do something with my denominator, because as I just showed, this 12 can be divided by that 6, which leaves me as d squared. All right, and as long as there are no radicals in the denominator, we're okay. All right, so this is simplified. Okay, this one's pretty tricky. You've got a radical inside a radical. I'm actually going to rewrite this as the sixth root of 8, and I'm going to raise that to the 1/2 power, right? Anytime I see a square root symbol, I know that's the same as raising something to the 1/2 power. It's a good thing to memorize. It's going to happen a lot later on in high school and then in college. And then I'm going to go ahead and rewrite this 8, or this sixth root of 8 as a fraction. That's 8 to the 1/6 power, and then raised to that original 1/2 power. And we learned in the last lesson that if you have a power raised to another power, you can multiply. That gives me 8 to the 1/12 power. That is simplified. If you wanted to write a radical, you could write that 8 with an index of 12. Those are the same thing. Okay, so that's it for that page. Let's keep going with some more. Some operations with radicals. I'm going to go ahead and ignore A. You guys can do that from your days in Algebra 1. In B, I have to have the same index, so they're trying to confuse you with this index of 3. That one has to be standalone by itself, because the other ones are the square root of 2, not the cube root of 2. So 5 root 2, so I'll do this one, 5 root 2 minus 4 root 2 is 1 root 2, and then plus the cube root of 2. All right, so the square root of 2 plus the cube root of 2, that's simplified. Okay, this one I'm going to break down 24, and if you remember your days in Algebra 1 or even Geometry 1, I know you guys did this last year, you're thinking to break down using your factor trees for 24, but be careful here. This is going to be a little bit different because the indices or index for each of these are 3. I'm going to try to think of factors of 24 and 81 that are actually going to be, I can take the cube root of, not the square root of, right? So when I think of 24, I know that I could break this down into 6 times 4, which has a perfect square of 4. But because the index is 3, I'm going to use 8 and 3 because I know the cube root of 8. So I'm going to break this down as to the cube root of 8 times 3 plus, same with this one here, I'm going to break down 81 into 27 times 3 because I also know the cube root of 27. So the cube root of 8 is going to be 2. So that's 2 times the cube root of 3 plus the cube root of 27 is 3 times the cube root of 3. All right, now they both have the same 3 that's inside. So I can go and add the numbers on the outside. The 2 and the 3 will add to give me 5 times the cube root of 3. So that's the simplified answer for C. Let's look at D. I'm going to multiply this square root of 7 times both. So 3, and now watch how I write it, times the square root of 7 times the square root of 14. I put them in the same radical. Minus, and this is going to be the square root of 21 times 7, right? Putting them in the same radical. All right, the order doesn't matter because it's multiplying. Now the 3 stays on the outside, but I can break down that 14 to be 7 times 2. And with this one, I can break down the 21 to be 3 times 7, and then bring down that original 7. So now what you hopefully learn in Algebra 1 is that if you have 2 inside, when your index is 2, that brings out on the outside you have 1. So 3 times 7 times the square root of 2 minus, same thing here, 2 on the inside. So 7 times the square root of 3. Multiplying the 3 and the 7 gives you 21 times the square root of 2 minus 7 times the square root of 3. And that's as far as you can go because your radicands, the numbers inside the radical, are not the same. Okay, same thing here. I'm going to multiply by the square root of 3 over the square root of 3. That will get the radical out of the denominator. So that's the square root of 18 times 3 minus the square root of 6 times 3 over, and that's just going to be 3. The square root of 3 times the square root of 3 is really the square root of 9, which is 3. I'm going to break down 18 and 3 to be 6 and 3. I'll break down this 6 here to be 2 and 3. Bring down the original 3 all over just a 3. So remember 2 on the inside, you pull out 1, so that's 3 root 6 minus 3 root 2 over 3. If you wanted to, they both have a 3 in front, so you could factor out that 3 to get root 6 minus root 2 over 3. The 3's cross out, which leaves you just root 6 minus root 2. Okay, last one on this page. All right, I'm going to multiply using FOIL here. 5 times 3 is 15. 5 times negative root 2 is negative 5 root 2. Plus 3 times root 32. Then minus, and just like I did before, keep the 32 and the 2 inside. Can't do anything with these right now. I can simplify that square root of 32. Right, if I do it over here, the square root of 32 breaks down into the square root of 16 times the square root of 2, which is going to be 4 root 2. So that's going to be 3 times 4 root 2 minus, we just did that one over here. So this one is going to be, break this down into 16 times 2 times 2, which actually you could have just put those together to get 64, which will give you a perfect square. So that's 12 root 2 minus, and as I just said before, that's the square root of 16 is 4. Then you have those two 2's come out to give you 1 2, that's 8, which makes sense. 16 times 2 is 64. The square root of 64 is 8 with no more radical. So let's combine the stuff like terms. So the 15 and the negative 8 will go together, and the negative 5 root 2 and positive 12 root 2 will go together. So that's 7 and then plus 7 root 2. Okay. Now, this last page is on just rationalizing denominators, which we already had a mini peek of that on letter E. All right, so I'll show you the most basic one you guys learned in Algebra 1 and probably reviewed in geometry. So times the square root of 6 over the square root of 6. So that's 3 times the square root of 6 over 6. Reducing 3 over 6 gives you the square root of 6 over 2. That's simplified. What your brain needs to know, not only how to do this, but also that this in a calculator, this in the calculator are the same value. This one is a little tricky because if I did the root 5 over root 5, the cube root of 5 over cube root of 5, you actually need to do another set, right? Because that will not get rid of the radical in the denominator. But now that you have 3 of them, the cube root of 125 is just 5. And then this is going to be 10 times the cube root of 25. All right, so that's simplified there. Actually, it's not. You can reduce and get 2 times root 25. There we go. Now it's simplified. Okay, I'm going to skip these next two and just do these last ones because they're the most complicated. When you have in the denominator not just a radical by itself, if you've got something added or subtracted with it, then you have to multiply by the conjugate. This is going to feel very similar to with imaginary numbers and operations when we did division, when we multiplied by the complex conjugate of the denominator, but these are not imaginary. So what you're going to do is multiply by the conjugate, where you write the 3 and you write the root 5 on top and bottom, but the sign is going to be opposite, okay? So in the numerator, I'm going to have 6 minus 2 times the square root of 5 over, now this is where, and I'll show you in class because I'm just going to ignore the oi in FOIL here. When you multiply by the conjugate, your middle pieces of your 4 terms that you multiply out are going to be opposites, right? So I really only need to focus on 3 times 3, which is 9, minus root 5 times root 5, which is going to be just a 5. So that's going to reduce to 6 minus 2 root 5 over 4. You can leave it like that. If you wanted to factor out a 2 in the top, you get 3 minus root 5 over 4, which reduces to 3 minus root 5 over 2. Okay? All right, so last one here, doing that same idea with the conjugate. I'm going to multiply x plus y and put the 4, right? So again, I haven't changed anything with the problem yet, but my sign of subtraction becomes addition. So in the numerator, I have x times the root of x plus y plus x times 4, which is 4x, all over, again, just the first parts here, the square root of x plus y times the square root of x plus y is just x plus y, and then that's going to be minus 16. All right, so that is the simplified version for f. All right, and so that's it here, guys. Hopefully you get some good practice with these radical expressions, but if you have any questions, please reach out.